Hello everyone. What we're going to do today is we are going to start learning inverses of our sine, cosine, and tangent functions. So what I want you to do for a second is I want you to think back to college algebra. What is an inverse? Well, if you remember in college algebra, an inverse is when we can interchange x and y. So for instance, y equals x plus 1, its inverse would be x equals y plus 1, so y equals x minus 1. So this would be the inverse of this. We just interchange x and y and solve for y. Now, this function right here had to be special. This one had to be a one-to-one function in order for it to have an inverse. Now, if you remember, how did we know if a function was one-to-one? Well, you did the horizontal line test. You laid your pencil across the graph, and if a horizontal line only crosses it in one spot, then it's a one-to-one function. If it crosses it in more than one spot, then it's not a one-to-one function. So, let's apply that same logic to our sine function. So, right here, let's draw our graph. And let's draw the graph of a basic sine function. Draw the graph of a basic sine function. Okay, looks something like this, if you remember. And so on. Alright, now, is this one-to-one? Well, all you've got to do is lay your horizontal line across this, and you figure out real quickly, no, it's not one-to-one. Look how many times it crosses. And it continues to cross infinitely in both directions. However, the whole sine function is not one-to-one. But if we restrict the sine function, we can overcome this problem. If we restrict its domain, we can make it into a one-to-one function. For instance, this right here is negative pi over 2. This right here would be pi over 2. If we restrict the sine function to that right there, to that green line right there, now that is a one-to-one function over that particular interval. Now this is y equals sine x from negative pi over 2 to pi over 2. So if we restrict it, it is one-to-one. Now, essentially what we're saying here is we're saying, okay, we know that sine of x equals 1/2 at infinite many places. You can find that answer infinitely many times across the sine curve. Sine x equals 1/2. However, we're just restricting it to this one particular interval here so that we know there's only one spot where sine x equals 1/2, and that's pi over 6 in that interval. Okay, so in that interval, pi over 6 is the only place where sine x equals 1/2. That's what we're trying to do here. We're trying to restrict the domain so that we only get one answer for our sine x so that it's one-to-one. Because if we find a one-to-one function, if we find that sine is one-to-one, this is what we can say. Okay? The inverse sine function when restricted to, when its domain is restricted from negative pi over 2 to pi over 2, we say that it's y equals the inverse sine of x. This is how we write it, inverse sine of x, or we can write it as y equals arc sine of of x. Arc sine and inverse sine mean the same thing. Okay? So either way. Now this is equivalent to, what is this equivalent to? This is equivalent to sine of y equals x. Now notice we're used to writing it as y equals sine x. But remember, with an inverse, you interchange your x and y's here. So this is the sine of y equals x for y in this interval. Okay? For y in this interval. Alright, so now, so we say this is the same thing as the sine of y equals x. We reversed our x's and y's for y in that interval. That is essentially what the sine function is. So to solve for y, we have to take the inverse of both sides. So that's how we solve for y in that particular function. So here's a t-chart, okay, of, all right, our x is going to be, let's not make this t-chart like this. Let me make it like this. Let me just make it like a table. Okay, so for the function y equals sine of x, all right, the point negative 1/2, 1, that point is on that function. Negative 1/2, excuse me, negative 1/2, negative 1. Negative 1/2, negative 1 is on that function. The point negative pi over 4, negative square root of 2 over 2 is on that function. Look at your unit circle. That's where I'm getting these values for. Or from, excuse me. The point 0, 0 is defined on that function. The point pi over 4 and square root of 2 over 2 is defined there. And so is the point pi over 2, 1. Now, back in college algebra, you learned something very specific about inverses. It's a very important characteristic. Because remember, a lot of times we can graph the original function, but if we tried to graph the inverse, it might be more difficult. So we had a rule in college algebra that said if the point AB is on the original function, then the point BA is on the inverse. So if that's the case, then what do I know about arc sine or the inverse sine? Well, I know very specifically that if negative pi over 2, negative 1 is on the sine function, then negative 1, negative pi over 2 is on the inverse. And I could go all the way down this table, reversing these points, because they are all on the inverse in reverse, okay? So a lot of times it's going to be easier for you to graph the original and then graph the inverse just by reversing the points. All right, so, but you've got to think about what that does to your graph, okay? Because normally, when you graph one of these, normally we do something like this, and we graph our negative pi over 2, negative pi over 4, 0, pi over 4, pi over 2, 1, and negative 1. We graph those on our line like this. And so it would start out, if you go by that basically a t-chart is what we just had. If you go by that t-chart, it's going to look something like this. Okay? That's from negative pi over 2 to pi over 2. Now, this is y equals the sine of x. Well, what if we want to graph y equals the inverse sine of x? Well, remember, it's just reversing the points, but that's a bit of an understatement, because if you reverse the points, that means you have to reverse your axes. So that means this is going to be pi over 2, and this is going to be negative pi over 2. This is going to be negative 1, and this is going to be 1. So see, you have essentially switched your axes for the inverse as well. So keep that in mind. You're not just switching points. You're also having to switch your labeling on your axis, because what that ends up giving you, if you plot the reverse order of the points from the first graph here, if you plot the reverse order, you get negative 1, negative pi over 2. You get negative square root of 2 over 2, negative pi over 4. You get 0, 0. You get the square root of 2 pi over 4, and you get 1 pi over 2. So it essentially looks something like this. Now, I'm not drawing it completely right there, human error, but it looks something like this. So what we say is this: the domain of the original, if you remember, is from negative pi over 2 to pi over 2. The range of the original, what's the lowest value? Well, it's negative 1. The highest value is 1. That would be the range. So, remember another characteristic of inverses. Another characteristic of inverses is that the domain of the original is the range of the inverse. I put y, that's because range is the y value typically. It's the range of the inverse. And the range of the original is the domain of the inverse. So that's another characteristic you need to keep in mind as you're going through this. Now, we do have some interesting little identities that go along with this. Alright, so since they're inverses, if we take the sine of an inverse, well, as long as x is between negative 1 and 1, then if we take the sine of an inverse, that's going to give us x. They essentially cancel each other out. If we take the inverse of a sine, well, as long as x here is between negative pi over 2 and pi over 2, then as long as that's the case, we equal x. Now, this essentially is reaffirming that we have inverses here. If you remember from college algebra, you had compositions of functions, and we learned that g of f of x, if g of f of x equals x and f of g of x equals x, then we have an inverse. That's basically what this is doing. It's just reaffirming that particular function. So we'll use some of these. I'll show you how to use some of these inverses, these things here in just a moment. So let's look at an example. Let's look at the arc sine, the inverse sine, of the square root of 3 over 2. Okay, what is this? Well, this is equivalent to the sine of y equals the square root of 3 over 2. So, remember what we're looking for here. With our inverse, y has to be between these two values. So your answer has to come between those two values. So what y value between these two has an x value of the square root of 3 over 2. Well, think of it like this. Look at your unit circle. What value has a sign? It has a sign that is square root of 3 over 2 that lies between these points. So if we're looking at our unit circle, and we're just looking at the part between negative pi over 2 and pi over 2, so which one between here has a sign that is square root of 3 over 2? Well, the sign of this point right here is square root of 3 over 2, and the x is 1/2, and that particular point is called pi over 3. So at the pi over 3 value, the sign is square root of 3 over 2. So where is sine square root of 3 over 2 between these two? Well, it's at pi over 3. So you're thinking in reverse. Okay, so let's look at another one. What about, let's write it a little differently so you get used to both ways. The arc sine of negative 1/2. So where is the sine? Where is the sine equal to negative 1/2 on this between pi over 2 and negative pi over 2? Well, if you look at this point right here, it has a sine of negative 1/2 and an x value of square root of 3 over 2. So where is the sine negative 1/2? That would be negative pi over 6. Now, some of you are going to have to fight this off. Some of you have learned the unit circle just as that particular point on the unit circle is 11 pi over 6. And some of you have just learned it as that. You have to learn it in negative direction to be able to do this. So you're going to have to be able to realize that negative pi over 6 and 11 pi over 6 are the same function. But we have to write it as negative pi over 6 because of our interval here. So the answer here would be negative pi over 6. Negative pi over 6. Okay, it's got to fit in our interval. So negative pi over 6. So let's look at another one. I'm going to give you several examples of this. And the only way to get good at this, folks, you're going to probably struggle a little bit here in the beginning of this. You're probably going to not like it in the beginning, but the more you practice it, the more this is going to become easier for you, and I think you'll understand it a lot better. So let's look at one of our identities. What if I have this? Now, before you jump right into saying it equals 1.2 because of our formula, you've got to remember something. You've got to remember, in order for this to equal x, our x value needs to be between negative pi over 2 and pi over 2. I can't write it there because of it needs to be between negative pi over 2 and pi over 2. So you need to punch out negative pi divided by 2 and get the decimal version. Punch out pi divided by 2, get the decimal version, and see if 1.2 lies between there. And it does. It lies in between those two. So because of that, because 1.2 lies in that interval, we can say that, I almost wrote x, we can say that this equals 1.2. The inverse of the sine equals 1.2 as long as 1.2 lies in that interval. All right, let's look at another one. Let's look at the inverse of 3 pi of the. Let's look at the inverse of the sine of 3 pi over 4. Alright, so now it's tempting to go ahead and write 3 pi over 4 down as your answer. Very tempting. But what you've got to remember is our x value, our x has to lie in this interval here. Okay? So does 3 pi over 4 lie in that interval? No, it does not. Now we know that that the sine of 3 pi over 4 is equal to 1 over the square root of 2, or square root of 2 over 2. So the inverse sine of the sine of 3 pi over 4 is the number in this interval, in negative pi over 2 to pi over 2, with the sign equal to this. So in other words, this 3 pi over 4 is not in this interval, so we can't use it. But we know the sine of 3 pi over 4 equals this. So what you have to do is find the equivalent angle in this interval here that has this as its sine. Well, which one is that? Which one is that? Well, that would be pi over 4. Pi over 4 has a sine of 1 over the square root of 2, or square root of 2 over 2. So because we have to have it in this interval, we would say that this answer is pi over 4. Now we just use the equivalent, okay? We know the sine of 3 pi over 4 is equal to 1 over the square root of 2. So you have to figure out what angle in this interval has an equivalent value of 1 over the square root of 2. And that's what we did, okay? It's all about finding equivalent angles. So be careful with that. Now, one last one, and we'll be done with the inverse sine part. And our next video will include the inverse of cosine. So, all right, this is cosine of an inverse sine. Well, then this is going to mean the sine of y equals 2/3. Where does the sine of y equals 2/3? So what we need to do is we need to draw a reference triangle. Okay, so our C here is going to be 3. And our, since this is sine, our north and south value here is going to be 2 for the 2/3. Alright, so what we need to do, we're trying to find this angle right here, this y. Alright, so first and foremost, what we need to do here is we need to find A. We need to find this side right here. This is our A. So use your Pythagorean theorem. A squared plus 2 squared equals 3 squared. And you get your A to be the square root of 5. Okay? So, what we're actually trying to solve here is where does the cosine of y equal the square root of 5 over 3. That's what you're actually trying to solve. Now, what you get here for your answer, what we just did is the answer. Now, your question is, how is that? Well, this is all centered around angle y here. And so once we found that value for the inverse sine, we were able to use it to get our cosine value. I hope that makes sense. I think I stated that in a confusing manner. I'm sorry if I did. I'm a little under the weather today. But basically what we're doing is you're drawing your reference triangle so that cosine of y excuse me, I'm so sorry. So that cosine of y equals this. So once we find once we draw that reference triangle and we use it to find our cosine value of square root of 5 over 3, we're able to find the cosine of that inverse. Okay? So, I know that's probably a little confusing. You don't actually have to find the y value to find the answer. Sometimes we think we have to find the y value to get the answer. We're just looking for the answer to the problem. We're not actually trying to find an angle here. We just use this to help us get our triangle. I hope I stated that in the beginning. I can't remember if I did or not. I've got that groggy, disconnected feeling, as we like to say. But we're not actually trying to find y. We're trying to find an answer. So we use this in here, to find cosine of y. We're not really concerned about this answer here. We used this answer to get to set up our reference triangle so that we could find this cosine answer here, because that's all we were concerned about, was the cosine answer. And as long as you're using the inverse to set up the reference triangle, we're able to find cosine using the inverse sine reference triangle here. So we were able to find cosine as the x value over the hypotenuse, remember? So that's how we were able to find the cosine answer. I hope that makes sense. It sounded kind of confusing to me even when I said it. If you didn't understand that, please ask questions. I'll try to explain it in a better way for you, even if I need to do another example. But we'll have more examples of these using cosine and tangent. So we'll have more opportunities for you to see something like this, okay? So this is going to be all for this video. There is a page in your book, page 292, that talks about calculator. Depending on the calculator you have, it could be different. So I want you to practice typing these in the calculator off page 292 in your book, and getting your answers, because that's going to help you be able to do some of the ones of these I ask you to do with a calculator, okay? So keep that in mind. Page 292, work through the calculator values example there with your calculator, okay? All right, so I'll see you in the next video.